So here is our goal for the end of this PowerPoint discussion is that you should recognize that there is a force between two electrically charged objects, and that force is a vector. That shouldn't be new to you. All forces are vectors, okay? Gravitational force is a vector, so is electrical force. You should be able to describe, compare, and contrast the methods of charging an object by friction, by conduction, and by electrostatic induction. You already know how to charge something by friction, right? You guys rub that wand with the fur. Yeah. Electrons, because of friction, will be ripped off of one thing and deposited on another thing. That's charging by friction. You should be able to understand and explain the use of an electroscope, because you've been using one. We'll talk a little bit more about that. You should understand that charge resides on the outside surface of a conductor, and that the net charge inside of a conductor is actually zero. And you should be able to use the formula for the electric force between point charges, also sometimes known as Coulomb's law. We'll talk about that today. Okay? So that's our goal. First, let's look at some basic fundamental rules of electricity. Okay? Some fundamental facts just about electricity that you should understand and know. One is that there are two kinds of electric charge. We call them positive and negative. And a basic phenomena is that things that have similar charges repel, and things that have opposite charges attract. Electrically charged objects exert forces through space. What we say, force over a distance. Gravity is the same way. Electricity appears to be the same way. Forces can be exerted without actual contact happening. You can be in proximity, and charged objects will either repel or attract one another. Electric charge is a conserved quantity. If something gains a certain amount of charge, something else must have lost an equal amount of charge. Charge is quantized. Quantized. What does that word quantized sound like? Quantity. Excellent. And what that means is that electric charge can only come in very discrete quantities. Think about this, for example, with what we've been talking about. Something is charged by giving electrons or by accepting electrons. Right? Imagine for a second an electron had a charge of 2. Forget about whatever it is, just 2 coulombs, okay? If I give something electrons, I can only give it 2 coulombs, or 4, or 6, or 8, or 10. I can't give it 1.5 electrons. I can't give it a charge of 3, or a charge of 5, or a charge of 7. It just can't happen. So charge comes in very discrete quantities. That's what it means to be quantized. All right? And finally, the force between two charges, something you should understand about this, it varies inversely with the square of the distance between them. Weird. The force exerted varies inversely with the square of the distance between them. This sounds very familiar to something we talked about earlier. Gravity. Remember, the force of gravity also varied inversely with the square of the distance between the masses. So there appears to be a commonality here. So let's look at some pictures. Oh, come on. Hey, there's a picture of my wife. Check this out. We were at the playground down outside of Grand Junction, right? She slid down this little plastic slide, and look at her hair. Craziness. Okay, so what happened? Static electricity. So let's think about it on a more atomic level. She slides down the slide. What's going on? There's friction. So she's either gaining or losing electrons. I don't know which one. Let's assume she's gaining electrons. So she's gained electrons from the slide through friction. So she's charged negatively. Does she want to stay charged? No, those electrons are repelled from one another. They want to get away. And look, they're trying to get away as best they can. They're going all the way out to the tips of her hair, trying to get back to that slide, which is now positively charged. Crazy stuff, okay? Please remember, negative things repel, positive things repel, positive and negative things attract, okay? Opposites attract, similar charges repel. Something that is neutral, something that is electrically neutral, does it have charge? Yes. It just has an equal amount of both. Please remember that. It has an equal amount. So this thing that is negative, does it have any positive charges? You bet. It has tons of protons in there, but it just happens to have more electrons than protons. This thing that's positively charged, does it have any electrons? Yeah, it probably still has billions of them. It just happens to have fewer electrons than it has protons, so it has an overall positive charge. Here is a different kind of an electroscope. The electroscope you've been using has a needle. Another type of electroscope is called a gold leaf electroscope, where you have a little ball, and a metal conducting bar, and then two little leaves of metal, usually made out of gold. If you charge that electroscope up, notice that the leaves will also have that charge, and then they will repel one another and push apart, and you can tell. And that's the purpose of an electroscope, is to measure if something has an electric charge, okay? Okay, so methods of charging something. There is friction. We talked about that. Rub, 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 rub. You can gain or lose electrons by doing that. Conduction is another method, and that requires contact. So when you charged up the rubber rod and you touched it to the electroscope, you notice that the electroscope became charged. That was by conduction. Okay, that was called charging by conduction. The third way to charge something is by induction. And that was part C of the lab you just did. You never actually touched the electroscope with a charged object. You just brought it near. And then you grounded the electroscope, and then when you removed everything, that electroscope had a charge. And it turned out it was charged oppositely from the original object. I want to draw some pictures to show you kind of what was going on here to make sure you understand that. That method is called charging by induction. And it ends up creating an opposite charge on the second object. Here's our electroscope. Recognize that the plate and the holder and the needle, they are an isolated system. They're not connected to the casing, okay? So they're isolated from the world around them. When you bring a negatively charged rod next to it, what did the needle do? It moved. Let's think about why. You bring the negatively charged rod near it. What happens to the electrons in the metal plate? What do they want to do? Are they attracted or repelled? They're repelled, so they have to go down. So they'll move down into here, and into here, and here, and here. And now notice that the needle and the holder have a similar charge, and therefore the needle is repelled. Now, if you actually take the charged rod and touch it to the electroscope, what happens? So those electrons, those negative charges on the rubber rod don't want to be near each other, and now they have a way to get off. They have a place to go. So some of these will actually jump off, right? And then when you take the rod away, what happened to the needle? It stayed charged because now the electroscope is negatively charged. It has an excess of electrons. That's charging by conduction. Okay? So we bring in a negatively charged rod. What did the needle do? It moved because those electrons wanted to go away. Great. Then you walk up and you touched it. Okay? What happened when you touched it? The needle went back to zero, and why? You give these electrons that were trying to get away a path to get away, and they actually go out you because you're grounding it. It's called grounding it or earthing it from IB terminology. Okay? So now they have a path to go, and then you break this connection. Okay? You remove the wand. And what happened to the needle? It moved back where? It moved at an angle, and why did it do that now? It lost electrons now. Okay? Kinda. Yeah, you can kind of think of it that way. If you zero the scale with something on it, it's going to be not at zero anymore. That's kind of what you've done there. This is charging by induction. And notice that the electroscope is opposite from what the rod was. The rod was negative. You now have a positive electroscope. Okay? That's charging by induction. There is another method of induction. Imagine that I have two conducting spheres, and I bring the charged rod next to it. Okay? And these are conducting spheres. What will the electrons on the metal spheres do? Jump where? Which side? Okay, so there'll be more electrons over here and a net positive charge over here. Notice I haven't made any contact yet, but I've induced polarity. I've induced positive and negative ends here. While the rod is nearby, if I was to separate these two, okay, and then take the rod away, notice now I'd have two charged objects. Even though I never touched them, I induced electric charge. Okay? But they're not touching anymore.
But they would still be able to do that.
They would then spread out on each of their spheres, yes. And they would be uniform on each sphere, but the left one would be positive and the right one would be overall negative. So in the lab, you had that pith ball, and you brought a wand next to it. What did the pith ball do initially? It jumped towards it. Let's think about why that would be. The pith ball is a conductor, surface of a conductor. So what's going to happen on the surface of the pith ball? The electrons will move over here, which will then induce, is the pith ball charged yet? No, but it's polarized, right? It's still overall neutral, but it's now polarized. And then what happens? Positive and the negatives attract. There's an attraction here, and the ball is attracted to the wand. And then what happens? Electrons jump off of here because they want to get away, and they're attracted, and then the ball is negatively charged. And then what does the ball do? Then it's repelled. Because it's a negatively charged ball and a negatively charged rod, they're repelling. Okay? That's ideally what should happen. Sometimes the ball sticks and doesn't go away, and I don't know why that's happening, but I wouldn't worry too much about that picture. Let's talk about this guy, Charles Augustin Coulomb. He was a French physicist. He studied electricity very extensively, and he came up with some amazing discoveries in the 1700s. Yeah, Monsieur Coulomb. The first thing he discovered was that the electric force between two charged objects is inversely proportional to the distance squared between them, and it's directly proportional to the charge on the objects. Again, what does that sound like? Gravity. And it is very, very similar to gravity.
It's like the liver song.
It's like the pancreas song, exactly. Because he made this discovery, he gets some things named after him, which is kind of cool. When you discover something, you can name stuff. And it turns out the unit that we use to measure electric charge is called the Coulomb. It's abbreviated capital C. Okay? The unit of electric charge is the Coulomb. And it turns out that a Coulomb of charge is a very large amount of charge. Okay? 1 Coulomb is the amount of charge on 6.25 billion electrons, or 6.25 billion protons. Okay? It's a significant chunk of charge. An average lightning bolt can happen and dissipate about 10 coulombs of charge. Okay? To give you an idea. So that's a lot of electricity. Yeah, it's a big amount. If you're experiencing a couple of coulombs of electric charge passing through your body, you're probably going to die very quickly. Okay, it's big. So in problems, we usually deal with microcoulombs and millicoulombs and things like that. Okay, because a coulomb is a huge amount of charge. But the one thing you really need to know, and it's in your data booklet if you don't remember this, is the charge on an electron. This is known as the elementary charge. Sometimes it's represented by the lowercase e. And it is how charged an electron is. And it is negative 1.6 times 10 to the negative 19th coulombs. The charge on a proton is positive 1.6 times 10 to the negative 19th coulombs. Okay? So Coulomb did some study, and he came up with a mathematical relationship that allows us to calculate how much force exerts between electrically charged objects. And we call that equation Coulomb's law. And it looks like this. F equals KQQ over D squared. Whoa. Which is very similar to F equals GMM over R squared. GMM over D squared. Okay? K is a constant. K is a constant. It is in your data booklet. Okay? It's not negative K. It's just K. And it's 9 times 10 to the 9th. What's that, Luke? Nm is newtons times meters squared divided by Coulomb squared. Okay? So how this works, this is an equation that allows you to calculate how many newtons of force exist between two charged objects. If you know two things. Well, three things. If you know this constant, that's nice. If you know how charged one object is, Q stands for charge. How many coulombs of charge an object has, times how many coulombs of charge the other object has, divided by the distance between them squared. If you measure charge in coulombs, and if you measure distance in meters, and you use K as 9 times 10 to the 9th, you will get a force in newtons. Okay? You'll be able to find out how many newtons of force exist. Notice that the equation for electricity, Coulomb's equation, and the equation for universal gravitation given to us by Newton, very similar. What are some similarities that you see?
Mass is replaced by coulomb.
Mass is, instead of mass, we're using charge. Yep. Now, it turns out there are two forms of Coulomb's law that, for some reason, IB throws in your data booklet. I'm going to show you this one again just so you have exposure to it, but it doesn't get used that much. Because it can be written in terms of this other variable. Instead of a constant k, we can use this other constant e sub 0, which is the permittivity of free space. And this is what it looks like. Recognize that this is not negative f, it's just a bullet. But this is the same thing as k. That's all it is. K equals 1 over 4 pi e naught. Okay? 1 over 4 pi e naught. And I guess the reason this is useful is because technically you're going to have different forces if electrically charged objects are in different materials. See what I'm saying? Because certain materials conduct electricity better than others. So you would have, technically, if I had charged objects in water, for example, I'd have a slightly different value for this, for E sub 0. This is the permittivity of free space, allows me to calculate the force if I'm in a vacuum, okay? But if I was in water or glass or milk or something else, then I would use a different value for E. Rarely, if ever, does this come up, but I just want you to know it's there, and you do have this information in your data booklet. Okay. Yes, this is the permittivity of free space, or of a vacuum, or of air. Okay, it would be different if I was talking about the permittivity of Jello. Yeah. Okay. Question, Con? No, just stretching. All right. Remember that force is a vector quantity. So if I have multiple charged objects and it says solve for how much force, let's say this positively charged object feels, it's a simple task of breaking it down into pieces and adding the vectors. What you would do is first, you would calculate how much force is felt here. Then I would figure out how much force is felt here. Then I would know that I would have my charged object feeling a force in one direction plus a force in the other direction, and I would add those vectors and find the net force. Okay? And if they're not in a straight line, you can still do it, because let's imagine that instead of being in a straight line, that they're more like this. Okay? I could still calculate the force here and the force here, and then I could add those vectors and find the net force. Okay? Still would work. Kyle, you had your hand up first. Okay. Charge distribution. How is charge distributed on an object? This was investigated by Michael Faraday, great physicist, and discovered some basic fundamental laws of electromagnetism. And what he found is that if I have a conducting sphere, the charge will actually spread itself out nice and evenly all around, which makes sense because those electrons, they're going to be repelled from each other. But he also found that the charge is found only on the outside of a conducting material. On the inside, it's always neutral. It's always neutral, which is kind of cool. And if something is irregularly shaped, then charge will accumulate in regions of greatest curvature at the pointed parts. That's where the charge is going to accumulate. So basically what Faraday showed us is that here, imagine this is a metal sphere. If I got it all charged up, let's say positively charged, you know, those are going to distribute themselves nice and evenly around, right? And inside, if I was to walk inside, I'd be totally fine. The charge would still be neutral. And again, if you think about electric charges wanting to, you know, they're repelled from one another, they're going to move as far apart as they possibly can, and the farthest place they can get is to the outside. So that kind of makes some sense. But if the conducting material is not uniform, charges will be concentrated at the points of pointage, right? So like right here, you have the greatest concentration. Over here, you have much lesser concentration of electric charge. Okay. So why does this matter to us? Like, what do we do with static electricity? Again, this was something that was, when people first discovered electricity, it was really cool because they can make sparks and do all sorts of neat tricks, and people pay money to see it, and it was kind of cool. But what does it really matter to us? Well, one of the things it does for us is it helps clean the environment. Okay, we use static electricity to clean the environment. For example, you have a factory that is burning, you know, let's say coal to make shoes. And so what do you do with all that smoke? Well, you don't want the smoke in your neighborhood, so you build a big smokestack. And the smoke from your coal-fired factory is going up and blows away, and everyone's happy because the smoke is no longer landing in your village. It just goes away. But then if you start having tons and tons of smokestacks, then that's not okay because we all live on the same planet. You guys know this stuff. But so what we do now is we put two metal plates inside the smokestack and charge them both immensely and oppositely. Okay? And as the smoke molecules fly up, when they get in between these things, the electrons go, whoa, and they're attracted, and the electrons go ping, and they go flying off. And then you're left with a positively charged smoke particle. And that positively charged smoke particle goes whop and sticks over here. And it sticks. And then the hot air rises, and the smoke is clean. Okay? It's a smokestack scrubber. And then every so often, you turn down the factory, and you go and you scrub this thing, or you just whack it, and all the debris falls down, and you collect it up, and you go and bury it, and voila. Okay? So it's kind of neat. Okay? Okay? It's kind of neat. What else do we do? What else do we do? Lightning. Lightning is God's use of static electricity. Okay? What else? Xerox machines. Xerox machines use static electricity. Every time you go in there and you put something on there and you push the button, you should think about this because it's crazy. The little light thing goes, right? Somehow it gets an image. It takes a static electricity image of your paper, puts it onto a clean sheet of paper, and then sprays it with ink, and the ink sticks to where the static electricity is. And then dries it, and then whoom, okay? Thank you for your positive outlook, Omri. That I don't know, but it uses static electricity to dictate where the ink goes on the page. We're not done yet, guys. We're really not done.
What are you doing, guys? Stretching.
Next time you want to spray paint your car, anybody that deals with auto mechanics and spray painting, they use static electricity to make sure the paint spreads smoothly and evenly. They charge the car, they charge the paint, spray it, and the spray paint is attracted to the car and spreads itself out nice and uniformly. So static electricity is used in a lot of different ways. Now, many of you, actually, you can try these practice problems at home if you want to.